Okay, in this video we are going to do section 6.3, separation of variables. And the title says, and the logistic equation. You know, as far as the AP test is concerned for Calc AB, we want to go as far as separation of variables. So the first bullet point here, recognize and solve differential equations that can be solved by separation of variables. The rest of these topics are in the book. They're covered in the later examples, but they would not be on the AB calculus, the AP calculus exam for Calc AB. They could be on there for the BC exam, but we're not worried about that. So in this section, we're just going to do the first 3 examples from the book. So consider a differential equation that can be written in this form. M of x, where m is a continuous function of x alone, and n of y, where n is a continuous function of y alone. And we also have the derivative of y with respect to x, and it's set equal to 0. So as you saw in the preceding section, for this type of equation, all x terms can be collected with the dx, and all y terms collected with the dy. And then a solution can be obtained by integrating. Integrate both sides. Such equations are said to be separable equations, and the solution procedure is called separation of variables. And below we have some examples of differential equations that are separable. So if we look here at this first one, the first thing we should do is subtract this x squared from both sides. So now it's on the other side as a negative x squared. And then we want to multiply through both sides by this dx. That takes it out of this denominator, so we just have 3y dy. And now we have a dx to go with our negative x squared. From this point we would anti-derive both sides. In the second example, I would first divide through by sine x. Cosine divided by sine is cotan of x. And then this y prime, I would convert that to Leibniz notation, dy over dx, and then multiply both sides by dx. So again, now everything is separate. You know, our x term is with the dx, and we have our dy over here, and you know there is a 1 in front of that. So if we did integrate this side, we would have just a y. And let's see here in the last one, what would we do first? Divide both sides by x, so that would be gone, and we'd have our 2 divided by x. And this y prime, again, we'd convert to dy over dx and multiply both sides by dx. So we'd be left with this, which we could integrate both sides separately. So in example 1, separate the variables and find the general solution of this. Remember, the general solution is going to be y equals something, and then we're going to have our plus c. So first thing we want to do is separate the variables and then integrate both sides. So let's see here, we have our quantity, x squared plus 4 dy dx equals x times y. And let's see here, let's divide both sides by y. So we're going to divide that out and have a divided by y over here. So we're going to have, and let's even write that as 1 over y. And then we'll have our x squared plus 4 term, our dy dx, equals, those have divided out, and we now just have an x. So let's see. Next step, multiply both sides by dx. This is now over here. And then here's our remaining term that has an x in it. So we're going to divide both sides by this and get x over x squared plus 4 dx equals, and now what we have left on the left side will be 1 over y dy. So the variables have been separated. We have our, we have our y's and dy's on the left. We have our x's and dx's on the right. Next step, let me even give myself a little more room here. Okay. We're going to take the antiderivative of each side. And let's just work on the left side first. Let's see, we have 1 over y dy, or we could have wrote that as dy over y, and that should stand out as the logarithmic integration form. So when we antiderive that, we're going to get the ln of the absolute value of y. And you remember when we did the section 6.2, we would have a plus c on there, but since we're anti-deriving both sides, we'll just anti-derive both and then put our plus c on the right side. And let's see what we have here. Almost looks logarithmic again. Our denominator is a function, x squared plus 4. Our numerator needs to be that function's derivative. What's the derivative of x squared plus 4? Well, that would be 2x dx. So we're going to have to tweak it with a 1/2 out front of the integration sign. So when we anti-derive 1/2, the natural log of the quantity x squared plus 4, and then we'll have our plus c. Do we need the absolute value bars? Whatever x is, we're squaring it and adding 4. So if it's positive, it will remain positive. If x is negative, it will become positive. So we can replace those absolute value bars with parentheses. And if we remember our properties of logs, we can move this up to the top, and that will become to the 1/2 power, or the square root of that quantity. The ln of the square root of x squared plus 4, and we have our plus c. And on the left is our ln of the absolute value of y. Remember, we want to get to y equals something. So how do we get this y sprung out of the natural log function? Well, we exponentiate both sides. The left and right sides have now become exponents above base e. And we could think about it this way. The exponential function, is it ever negative? If you just think about the graph real quick, here's our e to the x function. The basic e to the x function is never negative. So this is never going to be negative, so we could drop the bars right here. This is just going to become y equals. On this side, we have e raised to a big exponent, and in that exponent we have a plus sign. We are adding exponents. When do you add exponents? Well, that's when you multiply like bases. So we can sort of split this up into e raised to the ln of the square root of x squared plus 4 power, and e to the c power. Because again, when we multiply like bases, we add the exponents. So here we broke it apart. Here, the e to the ln will cancel. So we're going to have y equals the square root of x squared plus 4, e to the c power. E is just a number raised to an arbitrary constant. A number raised to an arbitrary constant becomes an arbitrary constant. And we might want to put this c in front of the radical. Y equals c times the square root of x squared plus 4 square rooted. That is our general solution, just like they were asking us to find. Separate the variables, integrate both sides. A lot of times you will have to do an exponential, exponentiate both sides, and solve for y equals c times something, or something plus or minus c. In some cases, it's not feasible to write that general solution in the explicit form of y equals f of x. The next example illustrates such a solution. If we wanted to verify the solution at the end, we would have to implicitly derive. So let's see what they gave us here. Example 2, given the initial condition, y of 0 equals 1. So that's just a point on the curve. And that point on the curve, we put in a 0, and out come a 1. Alright, let's take a better look at this. We have xy dx plus e raised to the negative x squared power times the quantity y squared minus 1 times dy equals 0. Looks pretty nasty, but it's not too bad to separate the variables. And in this case, I'm going to move this to the other side of equals and make it negative. So we're going to have e raised to the negative x squared power times the quantity y squared minus 1 dy equals negative x times y dx. And let's see, I might want to keep my y's on the left here and get my x's on the right. So let's see, I got a y here I want to divide out. So if I divide by y, I'm going to divide that out. And for now, let's make that 1 over y. That might be easier to see as we work on the rest of this problem. And the only thing left over here on the left with an x is e to the negative x squared power. So I'm going to divide that out. So I'm going to divide this side by e to the negative x squared power. And let's clean this up a little bit. Now this is gone. So we're left with 1 times y times this, or y squared minus 1 over y dy equals, and over here we're going to have negative x, and let's move this e to the negative power up and make that a positive power. E raised to the positive x squared power dx. Alright, I think we have our variables separated. On the left are y's and dy's. On the right are x's and dx's. So it looks like we're ready to go. Let me give myself a little more room. We're now ready to not exponentiate, excuse me. We're going to integrate both sides. Okay, so we antiderive both sides. And this, when we look at this integrand y squared minus 1 over y, it doesn't really look like it fits any of our formats. But if we break that into separate fractions, the first piece of the numerator over the denominator minus the second piece of the numerator over the denominator, and that would be dy. Let's just work on this left side until we're done here. So we haven't anti-derived it yet. Y squared over y simplifies down to y. And we're going to leave this as 1 over y, because that looks logarithmic to integrate. So, let me get rid of this in the middle. Got it. So when we actually take the antiderivative here, this is y to the first, raise the power by 1, divide by the new power, or multiply by its reciprocal, 1/2 y squared, minus, this is in logarithmic form, that'll be the ln of the absolute value of y. We've integrated the left side. The right side should be a little easier. This is in the form of e to some power, some composite function, e to the u. So our u is x squared. And when we derive it, du will equal 2x dx. We have a negative x dx, so we're going to have to tweak this a little bit. We want a positive 2x dx, so we're going to multiply inside by a negative to make this positive, and a 2. To balance that out front, we're going to have to multiply by a negative 1/2. So we are going to have a negative half here. And then when we integrate e to the u du, the du goes away, and we just have e to the u, or e to the x squared power. And we don't want to forget our constant plus c. So there is our antiderivative of the right side, and this is equal to. And I guess we could just leave it like that. That would be our general solution. General solution. You know, we can't explicitly solve this for y equals because we have a 1/2 y squared and an ln over here. If we try to exponentiate to get rid of this ln, it'll work, but we'll have an e raised to this power with a y in the top. And we could go back and forth in that, all day. So we can't write it explicitly y equals this, but we do have our general solution. And now we're going to go back and work. We were given that initial condition. Let me double check our directions here. Given the initial condition, find the particular solution. So yeah, we're just going to use our initial condition, solve for this c, and write our particular solution. So we plug in x's, or zeros for x, and 1s for y. So this becomes a 1/2 1 squared minus the ln of the absolute value. Well, we can drop the absolute value bars. It's a positive 1, we know that. Equals negative 1/2 e to the x squared power. X is 0, 0 squared is 0, and our plus c. So 1 squared is 1, times 1/2 is 1, minus natural log of 1 is 0, equals This will be a negative a half times e to the 0. Anything to the 0 power is 1. Negative 1/2 times 1 is negative a half plus c. So to solve for c, we add a half to each side. A half plus a half is 1. All that work to find out c is equal to 1. So what do we do with that c? We plug that into the general solution to get the particular solution. So this c is 1 we just found is going right there. So our solution will be 1/2 y squared. Actually, let me move this up here. 1/2 y squared minus the ln of the absolute value of y, and that's equal to negative a half e to the x squared power plus 1. This would be our particular solution. And to make it match exactly what they set up to be the example in the book, they get everything with the variable on the left, and we're going to leave our c on the right hand side of the equals. And then we're going to clear the fractions. So let's clear the fractions right now. Let's multiply everything by 2. When we multiply this by 2, the half goes away, and we're going to have a 2 ln of the absolute value of y. We multiply this by 2, and we just get a negative 1 ex squared, and this is going to turn into a 2. And now let's get all the variables on the left. So the y squared stays, minus properties of exponents. This 2 in front of the log can be the new exponent of the variable here, so that's going to become the ln of y squared. Since it's a quantity squared, it's never going to be negative, and we can drop the absolute value bars, the ln of y squared. We're going to add this term to both sides, so now it's going to be a plus e to the x squared power, and that's going to be equal to 2, our constant, times 2. Example 3, last problem or last example for section 6.3. Find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at any given point xy. So we have an initial condition, but they have not, handed us our differential equation. They've sort of hidden it in kind of a word problem. Find the equation of the curve. Find the equation means when we're done, we're going to have y equals something. And we're going to have not a plus c on it. We will have our particular solution given this initial condition. But it says find the equation of the curve that passes through the point and has a slope of this at any point. Well, what is a slope? A slope is the derivative, dy dx. dy dx is the slope, and that is equal to y over x squared at any given point xy. So there's our differential equation. We're going to separate the variables, integrate both sides, plug in our initial condition. So the way I would start this problem is kind of cross-multiplying, I guess you could look at it as. And let's see here. If I cross-multiply this way, I'm going to have dy times x squared. And that's equal to dx times y, or y dx. And I think for this one, I'm going to get my y's on the left. So I'm going to divide by y. And this is going to become dy over y times x squared equals dx. And then I'm going to divide both sides by x squared. dy over y equals dx over x squared. Are we ready to integrate? Might be easier to see it if we work a little bit more on these. The left side, of course, looks like a logarithmic integration. But over here, dx over x squared, if we think that's our derivative or our function, the derivative would be 2x. So we don't have a 2x dx for our du, so it's not going to be that. But let's write it with, maybe like this, a negative exponent. So on the left, we're going to leave dy over y like it is, equals, this would be x to the negative 2 dx. So here we're going to integrate with a simple power rule. We don't need logarithmic or anything else. So integrate both sides. Over here, the ln of the absolute value of y, and that's equal to, raise the power by 1, x to the negative 1 divided by the new power negative 1, and then we'll add our constant to the right-hand side. Let's see, divide by negative 1 is going to make this just into a negative term overall, and this x to the negative 1 power will drop to the denominator. 1 over x to the first negative equals the natural log of the absolute value of y, plus c. A little too far there. Okay, we're finding the equation of the curve, so it's y equals something, and right now our log is protecting our y in here. We want to break it out of there, and the way to get rid of the natural log is to exponentiate both sides. And again, here we have an e raised to an exponent that is a sum of two things. We get that from multiplying like bases. So here, well, an exponential is always positive. We can drop that and the absolute value bars, and that's equal to, here we will have our first term, e to the negative power 1 over x times e to the c. Because remember, when you multiply like bases, we would add these exponents. Negative 1 over x plus c is what we had up here. And e raised to a constant, some arbitrary constant, this is just going to turn into an arbitrary constant. So we'll have y equals c times e raised to the power negative 1 over x. And now we're ready for our initial condition. So let's get rid of this. This is our general solution. General solution. What gives it away is the constant, either the plus c at the end or the times c here. That's a general solution. This particular point we pass through will give us our particular solution. So our y is replaced with a 3, c is what we're solving for, e raised to the power negative 1 over x, x is 1. So that's 1 over 1, or 1, and it's negative 1. And let's see, we're solving for c, so of course we want to divide by e to the negative 1 power. E to the negative 1 power. So c is equal to, let's move this up and make that exponent from negative into positive. 3 times e. So that's our constant. What we just found is c, that we plug back into the general solution right here to find the particular solution. So as we rewrite this with our new c value, y equals, c has been replaced with 3e to the first, times e to the negative 1 over x. So we can work with that just a little bit more to get it to look a little more pretty. We are multiplying like bases. We have 3e. Multiplying like bases means we add the exponents. When we add these exponents, it's going to be 1 plus a negative 1 over x, or minus 1 over x. Let's come over here and do a little scratch work. 1 minus 1 over x. Well, we can rewrite 1 with a common denominator as x over x minus 1 over x, and we'll put that over the common denominator and have our numerator quantity as x minus 1. So y equals 3e to the power x minus 1 over x. And we have a little picture to go with it. This is our particular point that we went through, 1, 3, and the curve, remember, was created by the differential equation. The slope is y divided by x squared. So at any point you would take the y-coordinate and divide it by the x-coordinate quantity squared, and that would give you the slope that is occurring at that given point. And what we have here is our curve that just passes through that particular solution. This is where we stop section 6.3. If you want to continue to read 6.3 and read more about differential equations, be my guest.